I'm Jon Arne Hell. In English, I normally say Hall. It's much easier. Try to say Hell in US, it becomes difficult. Kind of draws attention, you know. I will speak a little bit about. It's too much volume. No. Oh, there. I was looking here. It was perfectly fine. I will say a bit about dynamic deepwater power cables or power umbilicals, quite related to what you heard just now. If you want to have a pump, you need a cable. That's where we come in. I will kind of go through what we've done in terms of qualifying this as a product for the subsea industry. One of the main issues here is that there are really no standards when it comes to power cables for subsea use. All standards are made for underground cable some 40, 50 years ago, and kind of the industry is still there. So we really have kind of almost started with a blank page, combining IEC standards and also then utilizing ISO 13628-5, which is the umbilical standard. But again, of course, creating a lot of discussions and knowing that Statoil has their specifics, Exxon has their specifics, Chevron has their specifics, and I mean there is no standard for that's to be perfectly true. Yeah. Too many things here. Okay. Well, background, more infrastructure on the seabed requires more electric power and hydraulic service. So basically what we did some 7, 8 years ago is that we set about with a qualification program internally to qualify power cables. Power in this sense, we're looking up to 36 kV, mainly to be used for subsea pumping. Now we've gone up to 52 kV for the O-score, so we kind of gone past it, but the aim at the time were 36 kV. We aimed at deep waters, mainly 3,000 meters. And at that time, we focused on AC system, meaning a 3-phase system for operation of the pumps. The whole development was done according to the DNV OSS 401 technology qualification, so we follow that in the qualification. We also used DNV to verify a lot of the work that we did during the qualification, which we found good because I mean DNV is a good discussion partner in most of these cases, and also when you're kind of missing a standard, it's always good to discuss with somebody that's not a company that has a bit more, well, I guess they have more access to data than most. Yeah, so what is the cables? Well, you see them here. It could be a power umbilical, it could be a inter-platform cable, it could be a DH, direct electric heating system, either as a concentric design or basically twice of a riser with two systems in one cable. Where we started was to, well, we were thinking Gulf of Mexico. For good reasons, we know that the first projects will probably come there for deep water. So that was the aim. So we started off looking at a vessel configuration with a lazy wave. And we took the assumption that we have a bend stiffener at the exit of the platform. For those of you who don't know that a bend stiffener, that's basically what you have on all cables, going out from a very stiff part to a fairly non-rigid part, as the cable typically is. The first issue we came to is really the fact that most power cables are made of copper. And to be perfectly honest, copper is kind of crap when it comes to strength. It's not good at all, and it changes quite easily. Another problem is that there is no industry standard again. As for tubes, as for a lot of the steel we use in typical umbilicals, there are international standards for S and curves. There are validated data available, and that really didn't exist for copper. So we started off basically qualifying copper as a material and testing it to the extent where we felt comfortable to put those models into our analysis programs. Meaning we evaluated all the dynamic effects, the creep effects, and then basically, well, maybe not very strange, but we quickly realized we need to reinforce the copper, or we need to protect the copper when we get to this water depth. It really can't take the strain it sees, because then you will have creep. And if you have creep, the copper will break quite easily. It will not survive if you get above the creep level, which can be debated, but it's not a very high amount of strain that before it goes into creep. So we decided on a concept after doing all the material testing, which basically focused on the copper itself. It focused on the insulation material and also the armoring materials. So when we'd done all the material testing, we went over to a concept phase where we were looking into the system design of the cable itself. And this is a very traditional cable. Most of you probably seen one. Normal three-phase cable. It has some profiles for making the cable round. It has steel armor, normal carbon steel armor, nothing fancy with this. And it has a couple of layers of polyethylene to protect it, and also to make it yellow and shiny for the client. You don't really need it, but they always want it. So we realized, as I said earlier, our normal technology wouldn't work. When I started in Nexans some 17 years ago, I learned a few rules of thumb that if you are to design a cable, you have to do it this and this and this way. And to be sure, if it did it that way, as I learned some years ago, this wouldn't work. So we kind of had to redefine the whole way we did design the cable. We had to redesign our tools. And we partially had to redesign part of our manufacturing equipment in order to be able to design it. So the first thing we did was basically to make a lot of different test cables, where we did, I'll push one more so you can see it. We have, when we make cables, what we call lay angles. This might be becoming a bit technical, but for you to understand, I'll say it anyway. This is the lay angle. That's basically how quickly you turn the faces. Basically, from going here, 360, you come here. You're basically making a spring. So what we did, we made actually more than this, but we made a lot of different cables where we combine either low lay length of the faces and high of the armor, and the other way around. And we kind of knew that a lot of these would fail. But that was the way to prove our modeling, that we could have cables that went to failure, and we were able to predict it with our analysis tools. So basically we did this, and we did a lot of testing. Mechanical testing, again then going back to the ISO 13628-5 and following all the mechanical test requirements from that specification. Doing flex fatigue testing, doing actual bend testing. We did rotation testing, we did elongation testing, crush testing. Well, basically what you need to do to prove your cable. Yeah, so where are we now? We have basically found the optimized solution, combining the different lay lengths. We focused on a 95 square millimeter copper conductor, which again covers most of the required pumps that we see today. For example, 3 megawatt as discussed earlier here. We did verify all our calculation tools. Again, we did this in quite a tight dialogue with DNV to get everything verified. We did make fatigue properties for all the conductors. This was done both in-house in fatigue test rigs, but also externally in other fatigue rigs. We did all the dynamic analysis to prove the integrity of the system for a 30-year lifetime. And we have done all the full-scale testing of the system after all the analysis work. Again, we have this in-house to be done in our plant in Holland. And we are basically ready for delivery. So then I was kind of wanted to look into what have we delivered or about to deliver. It's a project that's already been mentioned, Jack St. Malo. It's a project we have been working very closely with Chevron for many years. Chevron have done it very thoroughly. They just started off with a pre-feed. We did a feed, we did a qualification phase, and we ended up getting the project 3 years back. And this has been designed, and it has been qualified, it has been tested, it's been produced, and it's now about to be installed fairly soon. This system includes 36 kV power phases. It has hydraulic tubes with 15,000 psi working pressure. It has fiber optics. Looks like this. And you see basically the different items in there. What I do think is interesting when we come to this forum, and which I do think will make a difference in the industry in the future, is basically the fiber optic you see there. And that is basically a fiber that's put in there for temperature monitoring, a DTS system, but it's also done for strain monitoring, where you can monitor the strain in the bend stifter area. And basically, we are at the position where you can monitor the actual fatigue of the product when it's sitting or hanging on the floater in the Gulf of Mexico. And I think this is kind of a sort of a game changer for the cable industry. I think it's been more used in the riser technology previously, not as much in umbilicals, but in terms of predicting and keeping control of the lifetime of the umbilical, this is a very good tool. It needs to be further developed, but I think as for the first project where this is installed and it will be monitored during lifetime, I think it's a pretty good start in order to improve integrity management for this case, Chevron. I think another good example with Jack when it comes to standardization is really what ExxonMobil has done. They basically said we want the same. So they are making a copy. And I really do think this is the first time it ever happened. It is actually a copy. They are using the same pump, and they're using the same umbilical, and they're using the same suppliers, which is pretty uncommon for this industry. And I think it's a pretty good move by Exxon. I guess there's been a close cooperation with Chevron throughout the process, but this has been very good. Also, just to say something about how we did it. Also, just to touch this, we also done in cooperation with Chevron a pure power cable for subsea distribution. This looks a lot like the same as I showed you earlier, The big difference is the fact that you have much larger copper cores. And I think what really makes the difference here, the larger the copper, the more difficult it is to get it to survive. So in this case, you really have to go into the details of looking at friction effects in each and every copper wire inside your copper conductor. And that's really pushing our analysis tools to a new level compared to where we've been before. So I think the level of detail we do in analysis work today is kind of far beyond what we did only 4 or 5 years ago. Again, I do think we're delivering a much safer product today than we did 5, 6, 10 years ago. Going 10 years back, friction effects was kind of dealt with in an analysis report by saying friction is not seen as a negative effect. And that was the kind of the analysis you did. Well, fairly limited, that being said. Now this is the main focus when we do the fatigue analysis in cables or umbilicals. And we do see the effect is quite dramatic. And it probably should have been taken into account earlier than it really has. Yeah. So summary, we done the optimized the delay angles. We done the proper calculations. We established the fatigue properties and made our, let's say, our own standards. Performed all the analysis, and we qualified it according to ISO. I think now I have the possibility, so there were some discussions earlier today about ISO standing still, which I totally agree with. But there's a lot of oil companies here, so I take the advantage of saying it, because I think, a matter of fact, if I were to design a cable today, strictly according to ISO 63628-5, I'm quite sure that no oil company would buy it. They would say, this is not according to our specification, and we can't buy this. And for me, that's kind of a, well, knowing that that spec was released in 2009, it's 5 years away, we've gone pretty far away from utilizing the standard in a proper manner. I think we were much better off 10 years ago. Most oil companies did trust ISO standard quite good. Today, I don't think they do it. And I totally agree that we definitely need to do something about this, also in the umbilical cable side of the business. Again, also we need a new standard for power umbilicals or power cables, also for use in this industry. Okay. Questions?
Thank you. Any questions for Jon Arne? Don't be shy. Trond here have one.
Yeah, it's the question, man.
Someone has to stop.
Yeah.
The technology you're developing, it reminds me of a typical JIP project or a project qualification in a project, but you've done it in-house. And the result of it, it's your technology, or will it be used for someone else? Is it protected? Or?
I'm sorry to say, but I guess the most important parts are protected. I guess that also goes back to part of what was mentioned earlier about IP. I think it's fair to say that we try to protect our IP as everybody, including we see a lot of oil companies taking more and more patents on actual products. And again, the copper or making proper copper conductor are very process specific. So we would give away a lot of our process if we told too much. And the process itself is something we really would like to keep in-house. So our level of sharing the detail level is quite limited. And I think that's general for the industry.
And when you say that Exxon is copying what Chevron did, does it mean they have to use some of the same suppliers, or?
Well, they are, I guess.
I know they are, but do they have to, or can they select other?
Well, there were more suppliers in the qualification phase of Jackson model. So I guess in theory they could utilize what was gained of experience from that qualification phase. But to copy our product as is, I think it would be difficult for other suppliers.
Thank you. Any more questions? Nothing? Okay, then it's thank you for the presentation.
Thank you.